All right, let's dive right into this explainer. Today, we're totally flipping the script on algebraic identities. For a lot of us thinking back to math class, algebra feels like this giant, intimidating wall of equations and letters that just don't seem to actually mean anything. But today, we're going to transform those abstract strings of characters into tangible, highly visual tools that you can literally see. We're taking algebra off the chalkboard and putting it right in front of your eyes. It really begs the question, right? Is math just a rigid set of rules somebody's forcing you to memorize, or is it actually a series of hidden patterns just waiting to be discovered? It is incredibly easy to fall into the trap of thinking algebra is all about rote memorization. But what if I told you it's actually about uncovering the hidden structural realities of the universe? Seriously, once you see these patterns, you really can't unsee them. And suddenly, explaining this chapter stops being a chore and starts feeling like a superpower. So here's our roadmap for today. We're going to start with some mind-bending patterns, visualize them in 2D, blast into the 3D realm, apply them to the real world, and then finally build your ultimate visual toolkit. Let's get into it. Okay, Section 1, Patterns and Shortcuts. We're kicking things off by looking at a mathematical pattern that honestly feels a bit like a magic trick. It's the perfect way to introduce what an identity actually does in practice. Try this wild trick with me. Step 1, pick any 3 consecutive square numbers. Let's start small, say 1, 4, and 9. Now, Step 2, add the smallest and the largest squares together. So 1 plus 9 gives us 10. Step 3, subtract twice the middle square from that sum. Our middle square is 4, twice that is 8, so 10 minus 8. Step 4, boom, the result is 2. You probably think that's a fluke, right? Let's try it with bigger numbers. Take the squares 25, 36, and 49. Add the smallest and largest. 25 plus 49 is 74. Now subtract twice that middle square. 2 times 36 is 72. 74 minus 72 is 2. The result is miraculously always a constant 2. The crucial takeaway here is that this pattern isn't an accident. An algebraic identity isn't just some random rule or an arbitrary formula a mathematician made up to torture you. It is a universal mathematical truth. It's a structural reality about how numbers and, as we'll see in a second, shapes interact. When you know the identity, you skip the grueling calculations and just take the efficient shortcut. Moving on to Section 2, Visualizing 2D Identities. Let's see how this all builds up when we actually draw these concepts out. Welcome to two-dimensional Flatland. This is where it gets really fascinating, because we're translating algebra into pure geometry. Picture a large square. The entire length of one side is a, so naturally, the total area of this massive square is a squared. But notice how we've sliced that length a into 2 parts, a smaller segment called a minus b, and another segment called b. Those letters aren't abstract symbols anymore. They represent actual physical lengths on a square. And our goal here is to find the area of that gray square in the top left, which is a minus b all squared. So to isolate that gray square, you don't memorize a formula. You literally take the whole giant square, a squared, and you chop away the pieces you don't need. You subtract the area of the large red rectangle, you subtract the yellow rectangle, and through that physical geometric subtraction, you arrive at the famous identity, a minus b squared equals a squared minus 2ab plus b squared. By pulling away those smaller rectangles, we construct the algebra right before our eyes. No memorization required. You literally just picture a square being cut up. All right, Section 3, into the 3rd dimension. We've totally mastered the flat squares on paper, but the universe isn't flat. So let's escalate this. Let's add some depth and volume by moving into the 3D world. This next visual is an absolute game changer for one of the most intimidating identities out there, a plus b cubed. Imagine a transparent wireframe of a massive cube. The entire edge length of this cube is a plus b. So the total volume we're trying to fill is a plus b cubed. Tucked right inside, sitting in the corner, is our foundational building block, a solid blue cube with a volume of a cubed. But as you can see, the wireframe isn't full yet. Watch how we pack in additional shapes to fill out that total volume. We're slotting in these yellow and green rectangular blocks, or cuboids. Specifically, 3 yellow cuboids, each with a volume of a squared b, and 3 green cuboids, each with a volume of ab squared. We are physically packing a mathematical equation into a 3D space. It's like a giant puzzle. Now look at this explosion diagram. This is the true aha moment. When you pull that giant a plus b cubed apart, you see exactly what it's made of. one large blue cube representing a cubed, 3 yellow cuboids for 3a squared b, 3 green cuboids for 3ab squared, and finally that tiny little blue cube at the bottom to fill the last corner, representing b cubed. Seeing the giant cube break apart perfectly visualizes why the identity a plus b cubed equals exactly what it does. It's literally just a spatial inventory of those blocks. Section 4, Real-World Algebra. So we've physically seen why these rules work with shapes and volumes, but let's look at how they become insanely powerful tools for real-world calculations. Think of identities as literal cheat codes for real life. Say you need to find the square of 119. You could do it the long way, grinding it out manually on paper, risking a simple math mistake at every single step. But using the identity method, we can break 119 down into easy-to-manage chunks, 100 plus 10 plus 9. Then we just apply the identity for squaring a 3-part sum. We're taking a grueling multiplication problem and turning it into a series of incredibly simple, bite-sized additions. Because we broke it down, the math becomes something you can practically do in your head. The identity tells us to square the parts and multiply them together in pairs. So we instantly get 10,000 plus 100 plus 81 plus 2,000 plus 1,800 plus 180. Add those nice round numbers up, and we arrive at our answer instantly, 14,161. By understanding the geometry of squares, we bypass the heavy lifting entirely. And it's not just party tricks for mental math. Imagine you need to find the area of a walking path wrapping around a 40-meter square village playground. Or maybe you're building a rectangular pool. You know its total area is 2x squared plus 7x plus 3, and you need to figure out the exact length and width to buy your materials. These aren't just textbook tests. They are highly practical physical applications. You use your algebraic identities to factor those expressions, which literally gives you the physical dimensions you need to landscape that playground or pour that pool. Finally, Section 5, the ultimate toolkit. We've covered a ton of ground today, from magic number patterns to exploding 3D cubes. Let's wrap up this explainer by collecting everything we've visually proven into one place. Here is your ultimate visual cheat sheet. Before today, explaining this chapter might have felt like a really stressful memorization test of random letters and numbers. But now you know that x plus y squared is really just that large 2D square cut into 4 pieces. You know that x plus y cubed is just that 3D solid block packed with smaller colored cuboids. You aren't memorizing letters anymore, guys. You are remembering shapes. Which leaves us with one final, pretty wild thought. We've uncovered the geometric secrets of basic squares and cubes. But mathematics is a vast universe. If these intimidating algebraic equations are actually just beautifully structured 2D and 3D shapes, what other complex, terrifying formulas out there are actually just hidden patterns, waiting to be drawn, visualized, and finally understood? Keep looking for the shapes behind the numbers. Thanks for joining me on this explainer.